What happens if you keep turning the heat up, past the core of a star, past a supernova, past anything nature can actually reach? At some point, our familiar ideas about temperature break. Space, time, and matter stop behaving the way our equations expect. Physicists call that limit absolute hot, around 2.55 times 10 to the power of 32 degrees Fahrenheit, a temperature so extreme that our current laws of physics start to lose meaning. In this episode, we'll follow that question to its edge and see what theories say might happen there. If you enjoy slow, careful trips to the frontiers of astrophysics, a quiet like and subscribe helps this kind of content reach more curious minds. Get comfortable, and let's explore what it really means to talk about the hottest temperature the universe allows. Absolute hot is the name physicists give to the highest possible temperature the universe allows. To reach that idea, it helps to think about what temperature really is. At a basic level, temperature measures how much the tiny particles in a material are moving. In something cool, those particles move slowly. As you add heat, they begin to move faster, jostling, colliding, and spinning around. At the temperatures we meet in daily life, their speeds are far below the speed of light. Even deep inside the sun, where the temperature reaches tens of millions of degrees, the particles are still moving at only a fraction of light speed. If you imagine raising the temperature more and more, you run into a limit. No object with mass can move faster than light. It might sound as if that should be the top of the temperature scale, but it is not that simple. As particles approach the speed of light, their speed does not keep increasing in a straightforward way. Instead, their energy continues to rise. Their motion becomes more and more energetic without a big change in speed. That extra energy starts to curve space and affect time. At some point, the simple rules that work well for normal temperatures no longer apply. That critical point is related to what is called the Planck temperature. The Planck temperature is an enormous value, about 1.4 times 10 to the power of 32 Kelvin. In more familiar terms, that is around 2.55 times 10 to the power of 32 degrees Fahrenheit. This is what people mean by absolute hot. It is not the hottest temperature anyone has measured in a laboratory. It is the highest temperature at which our current laws of physics can still be used in a meaningful way. Above this, the theories we rely on begin to conflict with one another. At such an extreme temperature, the particles that make up matter would not simply move faster. They would carry so much energy that their gravitational effects would be as strong as the other forces that usually dominate at small scales. Quantum mechanics, which describes particles and their interactions at very small distances, and general relativity, which describes gravity and the shape of space-time, would both be equally important. Today, these two theories are used in different domains. We do not yet have a single theory that combines them fully. At the Planck temperature, that gap in our understanding becomes unavoidable. Our equations no longer give clear predictions. Even so, this temperature is not just an abstract number. The universe itself seems to have passed through this state. According to our best models, very soon after the Big Bang, before even a trillionth of a second had passed, the universe was at or above the Planck temperature. In that early moment, matter, radiation, and the structure of space were all mixed together in a way that we still do not completely understand. It was more than just hot gas. It was a state where the usual idea of separate objects may not have applied at all. That is part of what makes absolute hot difficult to picture. In everyday life, we are used to comparing warm and cold. We know the feel of a mild day, a hot stove, or steam rising from boiling water. But here, we are talking about conditions so far beyond experience that comparison starts to lose its meaning. Even the most extreme natural temperatures we know are nowhere close. Take one of the hottest known stars, often labeled WR102. Its surface temperature is estimated to be about 210,000 degrees Fahrenheit. That sounds huge, yet it is still unimaginably cold compared to absolute hot, which involves a number with 32 zeros after it. The difference is not like stepping from shade into sunlight. It is a shift into a part of physics that is entirely theoretical for us. No star can reach or hold this temperature. No human-made machine can come close. The only time it seems to have existed was in the earliest instant of the universe's history. When we try to think about such an extreme, our minds naturally fall back on familiar images. We might imagine ovens, volcanoes, blue-white flames, or the surface of the sun, but none of these come even close to the needed scale. At temperatures approaching absolute hot, atoms could not stay intact. The electrons would be stripped away. Protons and neutrons would not hold together. They would break into their smaller parts, called quarks, held by particles known as gluons. Even those basic building blocks might not remain as separate entities. The usual forces would begin to blur. In particle physics, there is a useful idea called unification. It suggests that at very high energies, some of the forces we treat as separate may actually be different aspects of a single, deeper interaction. In the world we know, there is the electromagnetic force, which governs light and electricity, the weak nuclear force, which plays a role in some forms of radioactivity, and the strong nuclear force, which binds quarks inside protons and neutrons. At extremely high energies, these forces may merge. Absolute hot lies near the region where such unification would occur. Gravity might also join in at even higher scales, though we do not yet have a full theory for that. It is tempting to think of temperature as a number you can keep turning up, the way you might turn a knob on a heater. In reality, temperature is tied to the average motion of particles. In a solid, atoms vibrate in place. In a liquid, they slide and roll past one another. In a gas, they range more freely. When you heat a material, you are adding energy to these motions. There is, however, a problem that appears as you approach the speed of light. Once particle speeds are already near that limit, they cannot increase much more. The added energy shows up in other ways, such as increasing the mass of the particles slightly and raising the overall energy density. This extra energy has gravity because energy and mass are connected. At the Planck temperature, the gravitational pull from that energy becomes strong even over microscopic distances. The particles no longer move in a fixed background. Instead, their own energy strongly curves the space-time around them. In normal conditions, we can safely treat gravity and quantum mechanics separately. We use general relativity to describe planets, stars, and galaxies, and quantum theory to describe atoms and smaller particles. At absolute hot, that separation breaks down. Every bit of matter and radiation affects the shape of space-time in a way that cannot be ignored, and the quantum nature of those fields is equally important. This is why absolute hot is better understood as a limit of our models than as a practical temperature we could ever reach. Beyond it, we would need a successful theory of quantum gravity, a framework that unites general relativity and quantum mechanics into one consistent picture. Many ideas have been proposed, such as string theory and loop quantum gravity, but none have been confirmed in experiments. Until such a theory is found and tested, absolute hot marks the edge of what we can currently describe. The number itself, about 2.55 times 10 to the power of 32 degrees Fahrenheit, is a stand-in for as hot as the universe can be described using our present physics. Even trying to create such a temperature in a controlled way does not seem possible. If you tried to pack enough energy into a tiny region to reach it, the energy density would be so high that the region would collapse into a miniature black hole. That black hole would then evaporate almost instantly through a process known as Hawking radiation, releasing energy again. This behavior makes the limit self-enforcing. The universe does not allow you to hold a simple system at this temperature for any length of time. Cosmologists think that the only time the cosmos has actually been at or above this scale was during the Planck epoch, an unimaginably brief period, less than about 10 to the power of minus 43 seconds after the Big Bang. In that instant, the universe was extremely dense and hot. All the forces that now appear separate may have been unified. Space-time itself may have been subject to intense quantum fluctuations, constantly shifting on scales smaller than we can probe. It was not just that matter behaved differently. The very arena in which matter exists might have been changing in a restless way. So when we ask how hot absolute hot is, we are really asking about the conditions that go with it. It is not only about a large number on a temperature scale. It is about a state where the distinctions we usually make between particles, forces, and even the structure of space and time may lose meaning. It is a boundary built into our current understanding of the universe, as far from everyday experience as you can get. Absolute hot may sound distant and abstract, but it is woven into the history of everything that exists. Every atom in your body, every molecule in the air, every planet, star, and galaxy formed in a universe that once passed through temperatures close to this limit. That makes the idea feel less like a strange number in a textbook and more like a starting point. The cool air of night, the gentle warmth of sunlight on your skin, all trace back to an early time when there was almost nothing but intense energy at a temperature so high we can only describe it with theory. It is natural to ask what it would mean to move toward such a limit. Could anyone build a device that approaches absolute hot? What material would you even try to heat? At those energies, no solid or gas would remain stable. Atoms would fall apart, and even smaller building blocks would lose their usual identities. Long before you reached the limit, the idea of an object to warm up would stop making sense. That is why, in practice, scientists do not try to heat a single piece of matter to those temperatures. Instead, they use particle accelerators to study very small, very short-lived bursts of extreme heat. In machines like the Large Hadron Collider and the Relativistic Heavy Ion Collider, heavy atomic nuclei are pushed to nearly the speed of light and then smashed together. For a tiny moment, in a space smaller than the width of a human hair, the collision creates a state called quark-gluon plasma. This is a form of matter in which quarks, the basic pieces inside protons and neutrons, move freely in a kind of hot fluid held together by gluons. Temperatures in these collisions can reach around 7.2 trillion degrees Fahrenheit. That is far beyond anything in normal life, and similar to conditions in the universe when it was only microseconds old, after it had cooled just enough for matter to start forming in a recognizable way. Even so, these temperatures are still about 30 trillion times cooler than the Planck temperature. They give us a small glimpse, not the full view. To make sense of that gap, it helps to place absolute hot on a mental scale of temperatures. At one end, we have the world we know. A warm room might be around 70 degrees Fahrenheit. A hot day in summer can push the air above 100 degrees. Step into a sauna, and the air might climb toward 200 degrees, making your skin tingle and your breathing faster, but still within what a healthy person can handle for a short time. A household oven on high heat may reach 500 degrees. Hold your hand too near the open door, and the sharp wave of heat will make you pull back instinctively. Move higher, and you leave daily experience. The surface of the sun, even at a distance of about 93 million miles, warms your face in a few seconds. Its visible surface is roughly 10,000 degrees Fahrenheit. No living thing could survive there, and solid matter would not last. Deeper inside, at the core of the sun where nuclear fusion takes place, the temperature reaches around 27 million degrees. There, atomic nuclei move fast enough to overcome their electric repulsion and fuse, releasing the energy that eventually reaches us as light and heat. Beyond that, the universe can do more. In some exploding stars called supernovae, the collapsing core of a massive star is briefly heated to hundreds of billions of degrees. Under those conditions, nuclei are crushed together in ways that ordinary stellar fusion cannot manage. Heavier elements, such as gold, platinum, and many others, are built in a few moments and then spread into space by the blast. The same forces that destroy the star also seed future planets and, eventually, living bodies. The heat is strong enough to tear apart molecules, atoms, and even some of the dense states of matter thought to exist in neutron stars. Yet as intense as that is, it is still not the hottest we have measured. In the quark-gluon plasmas created in high-energy colliders, temperatures reach the trillions of degrees Fahrenheit for a fleeting instant. For comparison, these achievements on Earth and the wildest natural events we observe in space all sit far below absolute hot. The Planck temperature is so high that if you tried to show both it and a sauna on the same straight line chart, either the lower end would collapse into a flat line or the upper end would stretch off the page. The numbers are simply too far apart for our usual sense of scale. One way to picture the growth is to imagine a ladder where each step represents a 10-fold increase in temperature. Start around 70 degrees Fahrenheit for a room. The next step up is 700 degrees, like a very hot commercial oven. One more step gives 7,000 degrees, in the range of some cooler stars. Another step leads to 70,000 degrees, where metals would vaporize almost instantly. Keep climbing. 700,000 degrees. 7 million. 70 million. 700 million. The details of ordinary matter fade away and give rise to plasmas and nuclear reactions. Continue through billions, trillions, and quadrillions of degrees. Somewhere far up that imaginary ladder, long after familiar comparisons have broken down, you finally approach the Planck temperature. Because of this, physicists do not treat absolute hot as just another figure on the scale. They think of it more like the speed of light, a built-in limit. You might get closer in theory, but you cannot pass it in any simple way if our current understanding is correct. It is not mainly an engineering problem. It is a boundary drawn by the structure of the laws themselves. At that temperature, our two most successful theories, quantum mechanics and general relativity, both insist on being applied at the same time. Quantum mechanics is the framework used for the very small. It describes electrons, photons, quarks, and other basic particles. It deals in probabilities and wave-like behavior. Instead of saying exactly where a particle is and how fast it moves, it gives the likelihood of different positions and energies. In large systems at low or moderate temperatures, these uncertainties average out, and the world appears solid and predictable. The familiar objects around you still obey the underlying quantum rules, but you do not usually notice the fuzziness. General relativity, by contrast, is the theory used for the very large. It explains gravity not as a pull in the usual sense, but as the bending of space-time by mass and energy. Planets, stars, and galaxies follow curved paths in this warped space-time. The theory is precise and geometric. It has been tested in many ways, from the motion of planets to the bending of light around massive objects and the timing of signals from distant pulsars. It also gives our best description of black holes and the overall expansion of the universe. Most of the time, these two theories occupy different domains. When you calculate the orbit of a planet, you use general relativity and can ignore quantum effects. When you compute the energy levels in an atom, you use quantum mechanics and do not need to worry about the curvature of spacetime. The small and the large can be treated separately. There is no conflict as long as they do not both need to describe the same situation in detail. Absolute hot sits exactly in the region where that separation fails. At the Planck temperature, the energy of each particle is so great that its gravitational influence can no longer be ignored, even over extremely tiny distances. Mass and energy are two forms of the same thing. As you add more heat, you add more energy, and so more effective mass. Pack that into a small enough region, and space-time itself begins to warp strongly at microscopic scales. In that environment, quantum rules and gravitational curvature are both essential. When physicists try to push their equations into this regime, they run into serious problems. The math can produce infinities, numbers that blow up instead of staying finite. In physics, such infinities usually signal that a theory is being used outside its proper range. They are like warning lights that say, this description is no longer reliable. At these extremes, quantum mechanics tells us to treat fields and particles in one way, while general relativity demands that we track how their energy reshapes space-time. The two approaches are written in different mathematical languages, and combining them directly often fails. This is why researchers say that the Planck temperature is a limit of our current understanding. Below it, even at very high temperatures, we can use known physics with good confidence. Above it, we would need a complete theory of quantum gravity, one that unifies quantum mechanics and general relativity into a single, consistent framework. Many ideas aim at this goal, including string theory and loop quantum gravity, but none have been confirmed by experiments so far. As a result, absolute hot marks a boundary where our descriptions become speculative. The connection to the early universe makes this limit even more important. In the first tiny fraction of a second after the Big Bang, the cosmos was so compressed that the average temperature is thought to have reached the Planck scale. Space expanded quickly, and the temperature fell. But for a brief instant, everything was as hot as physically possible. Every particle, every field, and every fluctuation in space-time was part of one dense, energetic whole. Later, as the universe cooled and grew, that early heat left subtle traces. We see hints of that past today in the cosmic microwave background, a faint glow of radiation that fills the sky in all directions. Its smoothness and tiny ripples carry information about conditions in the young universe, the way galaxies are spread out in space, and the mix of elements we observe in stars and gas clouds also reflect the cooling history that followed. In particle accelerators, when we reach slightly higher energies than before, we sometimes find behavior that helps refine our models of those early times. Each new step in temperature, though far below the Planck limit, gives another clue about the rungs above. For these reasons, absolute hot is not just a curiosity at the edge of a chart. It is a marker that guides our search for the deepest laws of nature. Absolute zero, the lowest possible temperature, shows us the limit of stillness and order, where motion nearly stops and quantum effects become very clear. Absolute hot points to the opposite extreme, where motion and energy are pushed so far that our usual ideas about particles and forces begin to fail. Together, these two ends of the scale suggest that there are boundaries beyond which our familiar concepts do not apply. From this point, it is natural to wonder what matter is actually like as you approach that upper limit, and how the laws of physics behave when space-time itself starts to shift at very small scales. At ordinary temperatures, even at values we call extreme in daily life, the rules of physics feel steady. We can describe how heat flows from one object to another, how solids expand when warmed, how particles in a material move faster as energy is added. Whether you are boiling water on a stove or calculating the conditions inside a steel furnace, the same basic ideas still hold, even when we move into the millions or billions of degrees, as in the cores of stars or the beams of particle colliders. Our theories remain useful, though we need more advanced versions of them. Nuclear physics helps us explain fusion in the sun. Particle physics helps us model the behavior of quarks and leptons when they are smashed together at high energies. But at the far end of the temperature spectrum, near absolute hot, the reliability of these separate tools begins to break down. The physics of too hot does not just mean a more complicated version of the same equations. It means entering a regime where quantum mechanics and general relativity both demand full attention. One theory treats matter and energy as quantum fields with built-in uncertainty. The other treats gravity as the smooth curvature of space-time. Together, at the Planck temperature, they push us to ask new questions about what space and time themselves truly are. At the temperatures we have been talking about, the idea of temperature itself starts to change. In daily life, we treat it as a simple measure of how fast particles are moving. But if those particles carry enough energy to noticeably bend the space they move through, then temperature is no longer just about motion. It becomes tied to the geometry of reality. In principle, the distances between particles could stretch or shrink. Tiny regions of space could ripple. Time could flow at slightly different rates in different parts of the system, even over scales much smaller than an atom. We cannot reach such conditions in a laboratory, but when physicists extend their equations to these extremes, these are the kinds of effects that appear. One consequence of this extreme energy density is the possibility of microscopic black holes. If you pour enough energy into a very small volume, the gravitational pull of that energy can become so strong that not even light can escape. In theory, at around the Planck temperature, the energy density could be high enough for tiny black holes to form. They would not resemble the large black holes in space that swallow stars and last for billions of years. Instead, they would be brief, forming and evaporating almost immediately through a process known as Hawking radiation. These short-lived objects could appear and vanish in far less than a trillionth of a second, but even their flickering presence would change the way heat and energy move through the system. This leads to a strange possibility. Near absolute hot, the familiar definition of temperature might stop being useful. Temperature assumes that you can talk about the average energy of a group of particles, but if the particles are constantly turning into tiny black holes and back again, or if space-time itself is fluctuating violently, then it may be hard to say what a particle even is. You cannot take an average over ingredients that do not stay well-defined for long. At the very highest energies, what we call particles might dissolve into something more basic. Perhaps the vibrating strings of string theory, loops of space-time and loop quantum gravity, or some other structure that has not yet been discovered. If that picture is right, then absolute hot is less like the top of a thermometer and more like a doorway into a completely new description of what is real. Physicists care about this, not only because it is a curious idea, but because the early universe almost certainly passed through such a state. In the first instant after the Big Bang, the cosmos was at or near the Planck temperature. Whatever happened during that moment set the starting conditions for everything that followed. How matter and energy were spread out, how space-time was shaped, and how the fundamental forces behaved as the universe cooled. If we could understand the physics of too hot, we might gain insight into why the universe expanded as it did, why matter appears in the amounts we see, and whether space-time is smooth or has a fine grain at very small scales. We cannot recreate the Planck temperature directly, but we can look for hints. High-energy particle experiments push matter to higher and higher energies, watching how it behaves at smaller distances and shorter times. Observations of violent cosmic events, such as gamma-ray bursts, black hole mergers, and the detailed patterns of the cosmic microwave background, show us how the universe behaves in its most extreme environments. The hope is that somewhere in these datasets, there are fingerprints of the deeper physics that takes over as we approach absolute hot. For now, the Planck temperature stands as a horizon for understanding. It is like the event horizon of a black hole, a boundary beyond which we cannot yet see. We can estimate its value, and we can describe how close we might get, but what lies beyond remains unknown. Before going further up the scale, it helps to step back and look at what temperature really means. In everyday life, we use the word casually. We check the temperature in the morning to decide what to wear, adjust a thermostat to make a room comfortable, or glance at a weather report when planning a trip. Behind these simple actions is a very precise scientific idea. Understanding that idea is key to seeing why there is a limit at the top as well as at the bottom. In its simplest microscopic form, temperature is a measure of the average kinetic energy of the particles in a substance. Everything around you is made of atoms and molecules that are always in motion. In a solid, they vibrate around fixed positions. In a liquid, they slide and roll past one another. In a gas, they move more freely, flying from place to place. The hotter the material, the more energetic this invisible motion becomes. The word average is important. At any given time, some particles move faster, some slower, simply by chance. Temperature does not describe a single particle. It describes the statistical average over a large collection of them. When you heat something, you are adding energy to these motions. You can do this by shining light on a surface, by placing a cold object in contact with a warm one so energy flows between them, or by compressing a gas so its particles collide more often. In each case, the typical speed of the particles goes up, and so does the temperature. In principle, If you could remove all kinetic energy and stop all motion, you would reach absolute zero, the lowest possible temperature. At that end of the scale, motion is as quiet as it can be. There is another way to think about temperature, used in thermodynamics. Here, temperature links energy to entropy, a quantity that measures how spread out energy is and how many different microscopic arrangements are possible for a system. In this language, temperature is related to how much the energy changes when the entropy changes. It acts as a kind of balance between energy and the number of ways that energy can be arranged. This view allows us to talk about temperatures even when it is hard to picture particles bumping around, such as the temperature of radiation in the early universe, the temperature of Hawking radiation from a black hole, or the temperature of the cosmic microwave background. In all these cases, we look at how energy is distributed over the possible states of the system. Temperature is also a bulk property. It only makes sense for groups of particles, not for individual ones. A single electron racing through space has energy, but we do not say it has a temperature by itself. Only when many particles are present, exchanging energy and reaching some kind of balance, does a well-defined temperature appear. This is one reason why exotic, short-lived states, such as the quark-gluon plasma in colliders, are so challenging to study. The system exists for a very brief time in a very small region. So applying the traditional concept of temperature requires care. Humans did not start with this detailed picture. For most of history, temperature was simply how hot or cold something felt to the skin. The first thermometers gave us numbers tied to practical reference points, like the freezing and boiling of water. Later, kinetic theory in the 19th century connected those readings to molecular motion. Once scientists realized that temperature reflects the motion and statistics of particles, many puzzles became easier to explain. Gases expand when heated because faster molecules push harder on their container. Materials change phase, melting or boiling, because added energy lets particles break or form bonds. Even reaction rates in chemistry can be understood by asking how often particles collide hard enough to react. What is remarkable is how well these ideas work across a huge range of conditions. The same basic statistical rules describe air in a room at around 70 degrees Fahrenheit and plasmas in fusion experiments at millions of degrees. Only near the extremes, close to absolute zero or near absolute hot, do new layers of physics begin to dominate. Near absolute zero, quantum effects lead to unusual states such as Bose-Einstein condensates, where many particles act as one. Near absolute hot, the gravitational effects of energy become so strong that space-time itself must be included in the description. Temperature is closely linked to the laws of thermodynamics. The first law states that energy is conserved. When you add energy to a system, you may change its temperature, its internal structure, or both. The second law says that unless work is done, heat flows from hotter regions to colder ones, and total entropy tends to increase. These principles apply whether you are deciding how long to boil water, designing an engine, or modeling the interior of a star. They also lead to some subtle effects, such as systems with so-called negative temperatures, where more particles occupy high-energy states than low-energy ones. These systems are not colder than absolute zero. They are, in a sense, hotter than any positive temperature. This shows that even a familiar word like temperature carries layers of meaning. Putting all this together, we can see more clearly why absolute hot represents a fundamental limit. Temperature, as we use it, depends on having a well-defined collection of particles in a space-time background that is stable enough to talk about average energies and energy distributions. At the Planck temperature, space-time itself is expected to fluctuate strongly because of the enormous energy density. The notion of a fixed background with particles moving through it becomes shaky. In that regime, the standard language of temperature, motion, and entropy may no longer apply in its usual way. This is why physicists view absolute hot not only as a physical bound, but as a threshold where our current concepts begin to fail. Once we understand temperature in this deeper sense, it is easier to see why it cannot grow without limit. One of the key hints comes from a basic principle of relativity. Nothing with mass can move faster than the speed of light in a vacuum. This speed limit is not just a technical detail. It is built into the structure of space-time. Because microscopic motion is tied to temperature, that limit eventually matters. Under normal conditions, such as air in a room or molten metal in a furnace, particle speeds are far below light speed. Even in the core of the sun, where nuclear fusion is ongoing, individual particles move at only a small fraction of that ultimate speed. As you raise the temperature, their kinetic energy increases and they move faster, but there is a lot of room before they get close to the limit. At extremely high temperatures, particles begin to move at relativistic speeds, where special relativity becomes important. In this regime, as an object with mass moves faster, adding energy does not increase its speed in the simple way it does at low speeds. Instead, the extra energy shows up as an increase in its relativistic mass, or more precisely, in its total energy content. You can keep feeding energy into the system, but you get smaller and smaller gains in speed. Most of the added energy goes into raising the energy density rather than making the particles move significantly faster. Because energy and mass are equivalent, this growing energy density has gravitational effects. At ordinary temperatures, the gravity of individual particles is so tiny that it can be ignored. But at extreme temperatures, where many particles carry enormous energies in a small region, their combined gravity can curve space-time noticeably, even over very short distances. At the same time, the speed of light limits how quickly heat can move. Energy can be transferred by particles bumping into each other, by bulk flows of material, or by radiation. Collisions and flows are limited by the speeds of the particles themselves. Radiation, carried by photons, travels at light speed, but even that is an upper bound. At very high temperatures, this radiative transfer becomes the dominant way energy moves, carried by a growing sea of photons, whose energies are very high and whose density increases dramatically. The photons themselves still have to obey the same rule as everything else. They cannot move faster than the speed of light. As the temperature rises toward the Planck scale, particles do not just move quickly, they interact so strongly that they are constantly creating and absorbing photons. Those photons carry so much energy that their own gravity matters as well. In this regime, the limit on speed becomes more than a simple cap on motion. It becomes part of the link between relativity and thermodynamics. You cannot keep turning the temperature up without changing the basic nature of the system you are trying to heat. It can be hard to picture what this means, because the jump from ordinary to relativistic motion lies far beyond everyday experience. At room temperature, the average speed of air molecules is roughly 1,000 miles per hour, fast enough to cross a continent in a few hours, but tiny compared with the speed of light. In the core of the sun, protons move at a few percent of light speed, still well below the limit. Only when temperatures reach into the billions or trillions of degrees do particles get close enough to that limit that extra energy starts to change the rules we use. The speed limit for particles ends up setting an indirect upper bound for temperature. It is not that particles suddenly refuse to move any faster at a specific value on a thermometer. Instead, once you reach the Planck temperature, the density of energy in a region becomes so large that space-time itself has to respond. Adding more energy does not simply increase particle motion, it changes the stage on which the motion takes place. Space-time begins to fluctuate, quantum gravitational effects take over, and the idea of a steady, well-defined temperature starts to break down. High-energy experiments give us a small preview of this change long before we reach the Planck scale. In particle colliders, heavy ions are accelerated to nearly the speed of light and smashed together. The debris forms a quark-gluon plasma, a state in which quarks and gluons move freely instead of being locked inside protons and neutrons. This plasma behaves like an almost perfect fluid with very low internal friction and radiates energy mainly as very energetic photons and gluons. It is not just a hotter form of ordinary matter. It is a qualitatively different state. If you imagine turning the energy up even further, the wavelengths linked to the motion of particles would shrink. Eventually, they would approach the Planck length, about 1.6 times 10 to the power of minus 35 meters, which is thought to be the smallest meaningful length scale in physics. At that point, speaking of positions and paths in the usual way may no longer make sense. This is another way of saying that the speed limit of heat is not only about approaching the speed of light, it is about reaching a point where added energy reshapes the basic fabric of reality. There is a kind of symmetry between this upper limit and the lower end of the temperature scale. Near absolute zero, quantum effects prevent you from removing all motion. Even when a system is as cold as possible, its particles retain zero-point energy, a small, unavoidable quantum motion. At the hottest end, relativistic and gravitational effects prevent motion from increasing without bound. In both directions, the limits come from the structure of the universe, not from engineering problems or the difficulty of building better equipment. This connection is one reason the Planck temperature is so closely related to other Planck units, the Planck length and Planck time. All of these scales arise from the same three constants of nature: the speed of light, often written as c, Planck's constant, which controls the scale of quantum effects, and the gravitational constant, which sets the strength of gravity. When you combine these constants in different ways, you get natural units that mark the point where quantum mechanics, relativity, and gravity all become equally important. The Planck temperature is the thermal expression of that point. It answers the question, how hot would something need to be for all three pillars of modern physics to matter at once? As you approach this upper bound, heat becomes less about individual particles jostling and more about the collective behavior of fields, space-time, and energy itself. The speed limit on motion prepares the ground, but the gravitational effect of extreme energy density is what finally closes off the familiar description. In this light, absolute hot is not just a very large number. It is a marker where the deepest parts of our theories meet. In terms of value, the Planck temperature is about 1.4168 times 10 to the power of 32 Kelvin. In degrees Fahrenheit, that is roughly 2.55 times 10 to the power of 32. It is named after Max Planck, a German physicist who helped found quantum theory in the early 20th century. Planck showed that by combining fundamental constants like the speed of light, the gravitational constant, and Planck's constant, you can create units of length, time, mass, and temperature that do not depend on human choices, such as meters or seconds. These Planck units describe the scales at which quantum gravity effects cannot be ignored. The Planck temperature is not a value reached by heating an object and reading a thermometer. It appears when you ask, in the equations, at what temperature the energy of particles would be so high that quantum mechanics, relativity, and gravity must all be included to describe them. At low temperatures, increasing energy mainly speeds up the particles. At higher temperatures, their speeds get close to light speed, and relativistic effects become important. Push still further, and the energy density grows so much that space-time begins to curve noticeably even on very small scales. The Planck temperature marks the point where all those effects are unavoidable, and where the usual idea of temperature begins to lose its clear meaning. This scale is also tied to the smallest meaningful distance, the Planck length. When the energy of a particle corresponds to the Planck temperature, its associated wavelength is about the size of this length. At that scale, quantum fluctuations in space-time are large enough that you cannot talk about distance and duration in the normal way. The graininess of space-time itself becomes as important as the behavior of the particles moving through it. What makes this regime especially interesting is that it is where our two main theories, general relativity and quantum mechanics, must both be used at full strength. General relativity gives a smooth, continuous picture of space-time. Quantum mechanics brings in uncertainty, discrete energy levels, and probabilistic outcomes. At the Planck temperature, you cannot set either one aside. You need a single theory that unifies them, often called a theory of quantum gravity. At present, we do not yet know exactly what that theory looks like. Ideas such as string theory and loop quantum gravity are attempts to build such a framework. They aim to describe what happens at scales where the Planck temperature and other Planck units are relevant. If we had a successful theory of quantum gravity, we could make more precise predictions about the universe in its very first moments, less than about 10 to the power of minus 43 seconds after the Big Bang. For now, our descriptions of that time are based on informed guesses and partial models. The Planck temperature is not only a theoretical construct, it describes a condition the universe itself appears to have passed through. During the Planck epoch, a very early phase of cosmic history, the universe was so hot and dense that it was dominated by energy, not by separate particles and forces as we know them now. Gravity, electromagnetism, and the strong and weak nuclear forces may all have been unified. Space-time likely experienced rapid quantum fluctuations. The laws we use for stars, planets, and everyday matter would not have applied in any simple form. This temperature cannot be sustained in a calm, steady way. The energy density required is so high that any region at that level would either collapse into a black hole or expand and cool extremely quickly, depending on the conditions. In the early universe, a very rapid expansion known as inflation seems to have allowed the temperature to drop fast, making it possible for particles, atoms, and eventually galaxies to form. In a laboratory, even if we could focus that much energy into a tiny volume, the state would vanish almost immediately. You can think of the Planck temperature as a kind of thermal horizon. Just as an event horizon around a black hole marks a boundary beyond which our usual view of events breaks down, this temperature marks a boundary beyond which our current equations stop giving reliable answers. We can define it with mathematics and reason about what might happen near it, but we cannot yet describe what lies beyond using tested physics. The gap between this limit and the hottest temperatures we have created is enormous. The quark-gluon plasmas made in colliders reach trillions of degrees Fahrenheit, yet that is still about 30 trillion times cooler than the Planck temperature. Compared with the full scale, these lab achievements are only small steps, but each step teaches us more about particles and forces at high energies and gives us hints about what the upper end might be like. If we could observe or recreate conditions close to the Planck temperature in a controlled way, we might be able to answer some of the most basic open questions in physics. Does space-time have a discrete, grainy structure, or is it truly continuous? Are the different forces we see today simply aspects of one deeper interaction? Is our universe one of many, with the Big Bang just one event in a larger multiverse? These questions remain open because the physics that would answer them sits behind the Planck scale. The Planck temperature also marks a boundary for the concept of temperature itself. Temperature is defined as a statistical measure of motion and energy for a collection of particles. Near this limit, the idea of separate particles may no longer apply. Instead, there may be a restless mix of quantum fields, brief black holes forming and evaporating, and possibly new entities not present in our current list of particles. In such a setting, trying to define a simple average energy becomes difficult because the ingredients do not stay fixed in the usual sense. What is striking is that a simple question, how hot can it get, leads directly to this frontier. The Planck temperature is not just a huge figure on a chart. It stands at the meeting point of relativity and quantum theory, a place where our current descriptions of reality reach their limits. The number itself is not arbitrary. It comes directly from the fundamental constants of nature. If the speed of light, the gravitational constant, or Planck's constant had different values, the maximum possible temperature would be different too. This makes the Planck temperature a reflection of the way our universe is built. To reach it, physicists combine these constants into a quantity called the Planck energy, and then relate that energy to temperature. The details of the calculation are technical, but the key idea is simple. There is only one natural scale that includes quantum effects, gravity, and the speed of light all at once. The Planck temperature is that scale written in thermal terms. It is the high end of what is possible given the rules we have measured. Thinking about it this way changes how we see the size of 2.55 times 10 to the power of 32 degrees Fahrenheit. It is not just another very large number, like a national debt or a star count. It is more like the thermal version of the speed of light. Just as no object with mass can move faster than light in a vacuum, no system can have a well-defined temperature higher than the Planck temperature without entering a regime that our present theories cannot describe. And unlike many abstract limits, this one is not purely hypothetical. The universe itself appears to have reached it in its first instant. The way the universe looks today, the faint background glow of leftover radiation, the way matter is spread across space, and the detailed patterns seen in the cosmic microwave background acts as evidence of that early extreme state. Given all of this, it is natural to wonder why we never see the Planck temperature appear anywhere in the universe today. The simple answer is that the conditions needed to reach it are so extreme that they cannot last in a steady way. Inside stars, the inward pull of gravity and the outward push of heat reach a balance at much lower temperatures. Even in supernova explosions, where heat and pressure spike to incredible levels, the material expands and cools long before it comes close to the Planck scale. In particle colliders, we can briefly reach temperatures that would make stellar cores seem cool, but the hot region is tiny and disappears in a fraction of a second as the energy spreads out. In that sense, the Planck temperature seems to belong to a single moment in cosmic history, the very earliest instant after the Big Bang. It is also one time in a deeper sense. At this point, energy is so concentrated that our usual idea of temperature may stop working. The energy density is high enough that space-time is violently fluctuating. Tiny black holes could form and evaporate. The forces we now treat as separate may already be merged. In such a setting, talking about the average kinetic energy of particles becomes questionable because it is not clear that particles, as we define them, are even the right building blocks. This is why the Planck temperature is more than just the highest mark on a thermometer. It is a signpost pointing toward a different kind of physics on the other side. Above it, the usual landmarks, stable particles, separate forces, smooth space-time may give way to a regime we have never directly explored. It is a boundary in our theories as much as in the physical world. There is something quietly striking about the way this number appears. The basic constants that define it were measured in different kinds of experiments. The speed of light came from studies of electromagnetism and light waves. Planck's constant emerged from quantum experiments with photons, electrons, and atoms. The gravitational constant comes from measurements of how masses attract one another in laboratory setups and in observations of planets and stars. Each constant, at first, looks like it belongs to its own area. Yet, when you combine them in the right way, you get the Planck units, and from those, you get the Planck temperature. Separate threads of physics, pulled from very different experiments, tie together at a single point on the temperature scale. That connection is a reminder that limits are not only restrictions, they are also clues. The Planck temperature tells us that there is a deep link between energy, space-time, and quantum uncertainty that sets a maximum for heat as we define it. Understanding in detail why that limit exists will almost certainly teach us something fundamental about the universe. In that sense, the value of about 2.55 times 10 to the power of 32 degrees Fahrenheit is not just a cap, it is also a target in our search for deeper laws. Even if we cannot reach this limit directly, we can move toward it in indirect ways. Particle accelerators test how matter behaves at higher and higher energies, giving us snapshots of matter in more extreme states. Observations of energetic cosmic events like gamma-ray bursts and merging black holes show us what happens when nature compresses energy into small regions. Cosmology, by studying the earliest light we can see, the cosmic microwave background acts like a detective story, working backward toward conditions that once lay much closer to the Planck scale. Each of these paths gives us hints about how physics changes as we climb the ladder of temperature. To think about what might lie beyond that ladder, it helps to look at how modern physics describes matter at a basic level. When we talk about electrons, quarks, or photons, it is tempting to picture them as tiny balls moving through empty space, but the deeper picture uses quantum fields. In that view, each type of particle is a particular kind of field spread throughout space: an electron field, a photon field, several quark fields, and so on. Particles are ripples or excitations in these fields. Space is not just an empty stage where they move. It is filled with overlapping fields that can be excited in many ways. Even when there are no particles present in a region, the fields are not perfectly quiet. Quantum mechanics says they are always subject to small fluctuations. At everyday temperatures, these fluctuations are small, and we can think of particles as stable, well-defined excitations with specific masses and charges. In stars or in present-day high-energy experiments, the fields are still stable enough that we can treat them separately. The electron field stays the electron field. The quark fields stay distinct. and the forces between them follow known rules. As you move toward the Planck temperature, this separation may begin to break down. The energy of each excitation becomes so large that the differences between fields could start to blur. The clear labels we place on particles may lose their meaning. The underlying fields themselves might transform in more radical ways. The distinction between the four known forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, could also disappear. We already know that unification happens in stages at lower energies. At high enough energies, electromagnetism and the weak nuclear force merge into a single electro-weak interaction. Some theoretical models suggest that at still higher energies, the strong force joins them, forming a grand unified force. The Planck temperature lies far beyond those scales and may be high enough to bring gravity into the same unified picture. In that early, very hot state, there may have been a single interaction and a simpler, more symmetric set of fields. As the universe cooled, that symmetry could have broken, and the one force could have split into the four we observe today. In this view, the Planck-era universe was not filled with the familiar variety of particles and forces. Instead, it was governed by a more basic structure from which our current fields emerged as it expanded and cooled. The many particle types we see now could be different low-energy patterns of a single underlying system, much like different notes produced by one instrument, though the reality is more complex than that simple picture. At such high energies, space-time itself can no longer be treated as a smooth background. Quantum fluctuations become strong enough to distort it at very small scales. The same energy that excites the fields might create local distortions in space-time, perhaps even forming microscopic black holes that rapidly evaporate. In this regime, the separation between the fields and the geometry they live in becomes unclear. The fields influence space-time, and space-time influences the fields in a tight feedback loop. Some proposed theories of quantum gravity try to describe this situation more precisely. String theory suggests that the basic objects are not point-like particles, but tiny vibrating strings. Different vibration modes appear as different particles at lower energies. Near the Planck temperature, many or all of these modes might be excited, and the distinction between familiar particles could fade. Loop quantum gravity takes a different approach. It suggests that space-time itself is made of discrete building blocks, often pictured as tiny loops forming a network. At the Planck scale, this network would be as important as the fields it supports. Space and fields might merge into a single quantum structure. Although we cannot test these ideas directly at the Planck temperature, the early universe offers indirect clues. The fine patterns in the cosmic microwave background, the way galaxies cluster on large scales, and the behavior of the universe's expansion all carry imprints of the physics that acted soon after the universe left the Planck era. By measuring these patterns with increasing precision, cosmologists hope to narrow down which kinds of high-energy theories are possible and which are not. If we can better understand what happened near that limit, it may also help answer other deep questions. For example, why does empty space have the small but non-zero energy density we infer from the accelerated expansion of the universe? Why do the fundamental constants, the strengths of forces, and the masses of particles take the values we observe instead of others? Is the state of our universe stable over vast timescales? Or could it someday transition to a different state with different physics? The behavior of fields, space-time, and energy near the Planck temperature is closely connected to all of these issues. In this way, The maximum possible temperature is not just a curiosity at the edge of theory. It is tied to the structure of the vacuum, the values of the constants, and the long-term fate of the universe. By following the trail of absolute hot, we are not only asking how hot it can get, we are also asking why the universe is the way it is, and whether it might have been or might someday become very different. All of these questions connect back to the way quantum fields and gravity are arranged in our universe. Up to now, we have mostly talked about fields and particles trying to keep their identities at extreme temperatures. The Planck temperature adds another layer. It is the point where gravity stops being a quiet background effect and becomes an equal partner, reshaping everything in ways that push beyond our everyday intuition. In daily life, gravity is the force we notice most. It keeps us on the ground, guides planets around stars, and shapes the large-scale structure of the cosmos. But in particle physics, on the scale of atoms and smaller, gravity is usually so weak that it can be ignored. The strong nuclear force, electromagnetism, and the weak nuclear force dominate. A single proton's gravity is negligible in most calculations. That changes as energies rise. Because energy and mass are interchangeable, every increase in energy also increases effective mass. Near the Planck temperature, the energy of individual particles is so large that their gravity is no longer a tiny correction. It becomes central to the dynamics. We describe gravity using Einstein's general theory of relativity, where gravity is not a force in the usual sense, but the curvature of space-time caused by mass and energy. A massive object like Earth bends space-time, and other objects follow the resulting curves. Normally, you need a lot of mass or energy to create noticeable curvature. At the Planck scale, each particle's energy is high enough to bend space-time significantly in its own neighborhood. This creates a clash with the way quantum field theory is usually built. In quantum field theory, fields and particles live on a fixed background of space and time. That background is assumed to be smooth and stable. Probabilities, energy levels, and interactions are all calculated with that assumption. In general relativity, space-time is not fixed. It is part of the system, shaped by whatever energy and mass are present. When the energy density reaches the Planck level, the two pictures cannot be separated. The fields distort space-time, and the changing space-time feeds back into the fields. Both quantum theory and relativity demand to be applied at once, and neither was originally designed to handle the full influence of the other. At those scales, the geometry of space-time is no longer a calm, smooth surface. Quantum uncertainty suggests that it becomes jittery and granular. General relativity expects a continuous fabric. The mismatch produces a regime where our familiar tools start to break down. One possible result is that microscopic black holes could form frequently. Relativity tells us that if enough energy is packed into a small enough volume, a black hole will form. At the Planck temperature, particle wavelengths are extremely short and their energies extremely high. So many configurations can satisfy that condition. These black holes would be tiny, much smaller than atoms, and would evaporate quickly through Hawking radiation, releasing their energy back into the surroundings. If such brief black holes formed and evaporated all the time, space-time would not be smooth. It would resemble a restless medium in which small horizons appear and disappear rapidly. This picture is very different from the quiet geometry we infer at human scales, but it follows naturally from combining quantum effects and strong gravity. In this regime, gravity also changes how we think about temperature. When space-time is strongly curved, time flows at different rates in different locations. Since temperature is defined statistically and involves energy per degree of freedom over time, two observers in different gravitational environments might not agree on a temperature in the simple way we are used to. Relativity also tells us that not only energy, but pressure and stress contribute to gravity. In highly relativistic systems, where particles move close to the speed of light, the pressure can be enormous. At the Planck temperature, both energy density and pressure are so large that they significantly curve space-time. Under some conditions, this curvature can help drive very rapid expansion rather than simple collapse. This is one reason the early universe could change so quickly. Gravity at those densities is part of a feedback loop that can amplify small effects. These ideas suggest that there may exist a deeper theory in which gravity and the other forces are different aspects of a single framework. From that deeper point of view, the apparent chaos at the Planck scale might follow more orderly rules. With the theories we currently have, we only see pieces. We can build models in quantum field theory and in general relativity, and we can push them toward the edge, but they do not yet merge cleanly into one consistent picture. This difficulty also forces us to rethink what vacuum means. In quantum field theory, the vacuum is the lowest energy state of a field, still filled with small fluctuations. In general relativity, a vacuum is a region of space-time without matter, often treated as empty and smooth. At the Planck scale, these ideas meet. The vacuum might be neither empty nor smooth. Instead, it may be a dynamic quantum gravitational medium in which geometry itself is fluctuating. Some physicists use the term space-time foam to describe this. The idea is that on the smallest scales, space-time could be full of brief structures, tiny horizons, short-lived tunnels, and other features forming and vanishing in extremely short times. In such an environment, light might not travel along perfectly straight paths in the way we usually assume. Over large distances, even tiny variations could add up, slightly changing how signals move. The concept of a fixed speed of light might need subtle corrections at these scales, and the relationship between cause and effect could become less sharp. These are speculative ideas, but they are consistent with the notion that at the Planck temperature, gravity does more than just add another piece to the puzzle. It reshapes the entire setting. Once gravity begins to act this strongly, the physics that worked well at lower energies becomes unreliable. Particle properties, like mass and charge, may no longer be fixed. The forces that hold matter together might behave differently. The familiar idea of fields living on a background might have to be replaced by a description in which geometry and fields are two aspects of one underlying quantum structure. This is one reason the Planck temperature is so compelling to researchers. It marks a place where our best theories, quantum mechanics and general relativity meet, and clearly require a unified treatment. To ask where this extreme state actually occurred, we do not have to imagine a distant star or a hypothetical experiment. We look back to the very beginning of the universe, not the first second or the first trillionth of a second, but an interval so early that it is best described using Planck units themselves. This interval is called the Planck epoch. It is thought to have lasted for about 1 Planck time, roughly 5.39 times 10 to the power of minus 44 seconds. That span is so short that more Planck times fit into a single blink of an eye than seconds have passed in the entire history of the universe. During that brief epoch, the universe's temperature was at or above the Planck temperature. This was not heat in any everyday sense. It was an energy density so high that the very nature of space-time was in flux. Matter, as we know it, had not yet formed. Even the notion of particles may not have been meaningful. The quantum fields, from which particles later emerge, were themselves part of a rapidly changing geometry. Under those conditions, the four forces we talk about today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single interaction. The distinctions we now draw between them would not yet apply. As the universe expanded and cooled, that single interaction may have gone through a series of symmetry breakings, splitting step by step into the separate forces we see now. Each stage in that process would have been associated with changes in the behavior of fields and in the shape of space-time, along with significant releases or redistributions of energy. You can picture this in a very simple way as an early universe that began in a highly symmetric state and then lost symmetry in stages as it cooled. Unlike a solid object, though, the structure that changed was space-time itself, along with the fields defined on it. The energy density during this period is far beyond anything we can produce or directly observe today. Even the most intense cosmic events we know now, gamma ray bursts, merging black holes, and the cores of supernovae are gentle compared with the Planck epoch. Then, every region was in an ultra-energetic state. At the same time, the universe was expanding. That expansion was not slow or familiar. Conditions were so extreme that the usual ideas of distance and time may need to be applied with care. Quantum fluctuations in this early phase could have been amplified by gravity, creating tiny differences in density from place to place. Those small variations would later grow into large-scale structures, galaxies, clusters of galaxies, and the web-like patterns of matter we map today. The faint variations in the cosmic microwave background, the afterglow of the Big Bang, are believed to carry a record of those early fluctuations. By studying the tiny temperature differences in that background radiation, cosmologists infer information about the initial seeds of structure. These patterns are one of our best sources of indirect evidence about what the universe was like not long after it passed through the Planck regime. Describing the Planck epoch is challenging because we cannot use only quantum field theory, which assumes a fixed space-time, or only general relativity, which assumes a smooth geometry. Both assumptions fail. We need a theory that merges quantum mechanics with gravity to fully model this period, but such a theory has not yet been completed or confirmed. As a result, the Planck epoch remains one of the least understood intervals in cosmic history. We know it must have occurred, and we can outline some of its general features, but we cannot yet trace its details with confidence. Different theoretical ideas offer different pictures. Some suggest that high-density regions in this early universe might have formed tiny black holes that evaporated almost immediately, affecting the distribution of energy in subtle ways. Others propose that there was a kind of phase transition from a pre-geometric state into the smooth space-time we work with now, with the Planck temperature acting as a threshold. There are even models in which our universe could have emerged from a prior collapsing universe, with the Planck regime marking a kind of bounce or rebirth. What we can say with more certainty is that once the temperature fell below the Planck limit, the universe entered a new era. The violent quantum fluctuations in space-time began to calm enough for a smoother geometry to emerge. The forces started to separate into distinct forms. Conditions became stable enough for particles to appear with consistent identities, such as definite masses and charges. This transition happened very quickly, within tiny fractions of a second, but it set the stage for everything that followed. The significance of this brief period is hard to overstate. Every galaxy, star, planet, atom, and chemical bond ultimately depends on the physics that operated at and just after the Planck temperature. If the fundamental constants had been slightly different, or if the pattern of symmetry breaking had taken another path, the resulting universe could have been very different, perhaps without the complex structures we observe, or without conditions suitable for life. It is also important to remember that this was not a rare event in one corner of space. The entire observable universe today was once contained within that early hot phase. Every region we can see, no matter how far away, shares that common origin. This shared beginning helps explain why the universe looks similar in all directions on large scales, a property called isotropy. The smoothness of the cosmic microwave background is one of the strongest clues that we all arose from the same high-energy starting point. Even though we cannot recreate the Planck epoch in a laboratory, scientists continue to probe it indirectly. Detailed measurements of the cosmic microwave background reveal fine structures that encode information about very early fluctuations. Large-scale surveys of galaxies show how those fluctuations grew over time. High-energy particle experiments explore how forces might unify at energies below the Planck scale, filling in pieces of the story between the earliest instant and the later eras we can describe more directly. Together, these approaches help narrow the gap between what we know now and the physics that govern the universe at the Planck temperature, bringing us gradually closer to a coherent picture of those earliest moments. The challenge and the appeal of this hottest moment is that it is both an ultimate extreme and an origin. To understand it would be to understand the time when space, time, and energy first began to behave in the ways we now recognize. At that boundary, the temperature of the universe was not just a large number. It marked the divide between what our current physics can describe and what it cannot. Even though that phase lasted for only a tiny fraction of a second, it prepared the conditions for everything that came after. It is natural to picture absolute hot and absolute zero as the two ends of a simple scale, like the top and bottom of a thermometer. One is unimaginably high, the other unimaginably low, and in between is the range where stars shine and life unfolds. But these two extremes are not only opposite in value. Absolute zero, 0 Kelvin, which is about minus 459.67 degrees Fahrenheit, is the point where you have removed as much thermal energy as possible from a system. In classical thinking, all motion would stop there. Quantum mechanics does not allow that. Even at absolute zero, particles keep a small amount of motion called zero-point energy. This comes from the uncertainty principle, which says you can never know both the exact position and the exact momentum of a particle at the same time. You can cool substances in the lab to billionths of a degree above 0 Kelvin, but you can never quite erase that last bit of motion. The limit at the cold end is set by quantum rules that protect a minimum amount of activity. Absolute hot is the opposite situation. Instead of taking away energy, you keep adding it. At temperatures near the Planck temperature, particles are already moving at close to the speed of light. Putting in more energy does not make them much faster. Instead, it changes what they are and where they live. Fields that normally stay separate begin to blur. Space-time, which usually acts like a calm background, starts to respond strongly. At some point, increasing the temperature further no longer means more motion. It means changing the basic ingredients of the system. The limit at the hot end is set by relativity, gravity, and quantum effects working together. You can think of the two limits this way. At absolute zero, you are blocked by what you cannot remove. You cannot take away the last trace of quantum jitter. At absolute hot, You are blocked by what you cannot add. You cannot keep pumping in thermal energy without forcing space-time and matter into a new regime where our definition of temperature breaks down. One extreme is about the impossibility of perfect stillness. The other is about the impossibility of sustaining unlimited activity. The physics near each extreme also looks very different. Close to absolute zero, quantum effects such as superfluidity, superconductivity, and Bose-Einstein condensation become important. In some materials, resistance to electric current drops to zero. In others, atoms move together as one large quantum state. These cold systems become highly ordered. Many particles share the same wave pattern and behave as if they are a single object. Near absolute hot order of that kind does not survive. The system becomes highly excited in a deeper sense. It is not just particles bouncing faster, it is the categories of particle and force themselves that start to lose clarity. Gravity becomes as strong as the other interactions. The geometry of space-time wobbles. Instead of a neat quantum state for many particles, you get a restless sea of energy, fields, and rapidly changing geometry. The cold end makes the world simpler and more coherent. The hot end makes it less settled and harder to define. The ways we approach these limits in practice also reflect this contrast. To get close to absolute zero in the lab, scientists remove energy as gently and efficiently as they can. They isolate atoms from their surroundings. They use laser beams to slow atoms down or let the fastest ones escape so only the coldest remain. Step by step, they narrow the spread of energies until the system is as quiet as the laws of physics allow. To move toward absolute hot, even in theory, you would need to do the opposite. You would have to concentrate energy on a huge scale. In nature, this happens in the early universe, and in rare, violent events like some stellar explosions and collisions of compact objects. In the lab, the closest we come is by smashing heavy ions together at nearly the speed of light. These efforts inject as much energy as possible into tiny regions in short times. They do not make a system calm. They drive it into extreme states where familiar rules begin to soften. Thinking about both ends together shows that temperature is much more than a number printed on a scale. It is tied to how matter and energy organize themselves. At absolute zero, motion narrows down into quiet, collective patterns. At absolute hot, motion becomes so intense that it tears apart the structures that give particles their stable identities. Still, both limits are set by the same underlying idea, the constants of nature. Planck's constant, which sets the scale of quantum effects, helps define the cold limit. The speed of light, the gravitational constant, and Planck's constant together set the hot limit. In this way, the two extremes act like bookends for all possible thermal states in our universe. Between these bookends is the wide range where the richness of the cosmos appears. Stars burn, planets cool, gases condense, and life forms patterns, all in the space between nearly perfect stillness and almost maximal excitation. Nothing we observe reaches either end, yet both edges shape what can and cannot happen. The stability of matter that we rely on every day is also a product of this middle ground. At the temperatures we normally encounter, and even in the hottest natural places we can visit, matter keeps a clear identity. A hydrogen atom has one proton and one electron. A carbon atom has 6 of each. Protons and neutrons remain intact. The strong nuclear force holds quarks tightly inside those particles. Electromagnetic forces keep electrons bound to nuclei. Because the energies are moderate, the forces that define matter are steady and chemistry can proceed in predictable ways. As temperature rises, these boundaries weaken in stages. Heat a solid and it can melt into a liquid. Heat the liquid and it can boil into a gas. Push further to millions of degrees and you reach a plasma where electrons are no longer bound to nuclei. What is left is a gas of bare nuclei and free electrons, guided strongly by electromagnetic fields. Plasmas are common in the universe. Stars are mostly plasma. At still higher temperatures, in the trillions of degrees, even protons and neutrons can no longer hold together. The strong nuclear force, which usually confines quarks inside these particles, is overcome by the thermal energy. The result is a quark-gluon plasma, a state in which quarks and gluons move more freely. Particle colliders have created this state for extremely short times in tiny volumes. The properties we measure match what we expect the universe to have been like a small fraction of a second after the Big Bang. Even this is not the end of the story. As we climb higher on the temperature scale, theory suggests that the differences between some forces and particle types begin to blur. At energies above those we can reach now, the electromagnetic and weak nuclear forces merge into a single electroweak interaction. Many models predict that at even higher energies, the strong force would join them in a grand unified interaction. Near the Planck temperature, gravity itself may join this unified picture. The separate fields we use today for electrons, quarks, photons, and other particles might be different faces of one deeper structure. In that extreme regime, the idea of a particle with a fixed mass, charge, and spin may stop being helpful. Instead of a set of stable building blocks, you might have a basic high-energy state from which all lower-energy patterns can emerge as the universe cools. Matter, as we usually define it, might not exist there at all. There would only be energy, quantum fields, and a rapidly changing geometry of space-time. Seen this way, the loss of clear identity at very high temperatures is not just destruction. It may have been a necessary step in allowing structure to form later. When the universe cooled from its earliest hot state, symmetries broke, and distinct particles and forces appeared. The fact that matter has well-defined properties today could be the long-term result of that cooling and of the way the universe moved away from the Planck regime. Studying how matter loses its identity at the highest temperatures could therefore help us understand why it has the particular identities we see at lower ones. If we could trace in detail how the universe cooled from a unified state to the structure described by the standard model of particle physics, many deep questions would become clearer. We might understand why particles have the masses they do, why the forces have their particular strengths, and why some symmetries of nature are kept while others are broken. The difficulty is that the conditions where this happened sit far beyond anything we can recreate in a controlled way. The quark-gluon plasmas made in particle colliders are already extreme, but they are tiny and last for an incredibly short time. Any state closer to the grand unification scale or to the Planck temperature would require energies many orders of magnitude higher. That is far beyond our reach. For now, most of what we know about these early identity crises of matter comes from indirect clues. The way the universe looks on large scales, the behavior of very high-energy cosmic rays, and the structure of our best theoretical models. It may be that the very idea of matter only fully applies in the cool, expanded universe we inhabit today. In the first fractions of a second, when temperatures were at their peak, the universe might have been in a form where the distinction between matter and energy, or between particle and field, was not meaningful. That early state no longer exists, but its imprint remains in the forces that act inside atoms and in the large-scale arrangement of galaxies. As we think about conditions near the Planck temperature, we start to meet the limits of our own theories. These are not physical barriers like a solid wall. They are conceptual boundaries where our current tools stop giving reliable answers. On the one hand, we can write down a value for the maximum temperature about 2.55 times 10 to the power of 32 degrees Fahrenheit, based on combinations of the speed of light, the gravitational constant, and Planck's constant. The logic that leads to that number is clear. On the other hand, knowing the number is not the same as fully understanding what the universe looks like at that scale. At lower temperatures, we have robust frameworks. Quantum field theory describes particles and forces on very small scales, assuming that space-time is smooth and fixed in the background. General relativity describes the curvature of space-time itself, assuming that matter and energy can be treated with classical concepts. In the environments we can study directly, from laboratories to stars and galaxies, these assumptions work very well. Near the Planck temperature, both sets of assumptions begin to fail at the same time. Space-time is no longer smooth and fixed. It is subject to significant quantum fluctuations. The geometry depends on the energy, and the energy depends on the geometry in a tight feedback loop. In quantum field theory, calculations rely on a stable background geometry. In general relativity, the geometry is the main variable. When both the fields and the space-time they live in are fluctuating together at extreme levels, our equations turn into problems we do not yet know how to solve. This is the first barrier, the mismatch between our two best theories. For decades, physicists have looked for a framework that combines them. String theory suggests that the basic objects are tiny, one-dimensional strings, whose vibrations produce all particles and forces, including gravity. Loop quantum gravity tries to quantize space-time itself, treating it as built from discrete units. Other approaches, such as causal dynamical triangulations and related ideas, explore different ways of constructing space-time from simpler pieces. Each proposal has insights to offer, but none has yet produced a complete, experimentally confirmed description of the Planck regime. The second barrier is experimental. We can build colliders that reach energies high enough to create quark-gluon plasmas and to probe the electroweak scale. The temperatures involved are in the trillions of degrees, extraordinary by everyday standards. Yet the Planck temperature is roughly 20 orders of magnitude higher in energy. That is not just a big step. It is a gulf so large that no realistic machine, even if it were the size of a solar system, could bridge it with any technology we can currently imagine. Because of this, we have to rely on indirect evidence: the cosmic microwave background, the distribution and motion of galaxies, and the properties of high-energy radiation from space. A third barrier is more subtle and concerns language and concepts. The basic terms we use in physics, particle, wave, field, space, time, are drawn from experiences and experiments far from the Planck scale. At those extreme energies, the universe might not be made of particles in any recognizable sense. Space and time might not be continuous. They might be emergent, like temperature itself, which arises from the collective motion of many molecules. If that is true, trying to describe Planck-scale physics with our current vocabulary is like trying to explain quantum mechanics using only the ideas of classical mechanics. You can make analogies, but some essential features will always be missing. Related to this is the problem of infinities. In quantum field theory, naive calculations often produce infinite values. Physicists handle this using a method called renormalization, which, in simple terms, reorganizes the equations so that the infinities cancel, leaving finite, testable predictions. This approach works extremely well at the energies we can test. Near the Planck energy, however, the same methods break down. The presence of strong gravity tends to make the infinities worse, and our usual tricks no longer produce meaningful answers. When your equations yield infinity where you expect a finite quantity, it is a signal that the framework is being pushed beyond where it applies. For these reasons, many physicists view the Planck temperature not just as a maximum, but as a frontier. Beyond it lies a regime where our current theories are special cases of something larger that we have not yet fully uncovered. The fact that we can point to this frontier so clearly is useful. It tells us where new physics must enter if we are to have a complete description of the universe, from the smallest scales to the largest. There is an interesting contrast here. At everyday temperatures, we can predict the behavior of matter with high precision. Near absolute zero, we can also predict how quantum systems will behave, often in exquisite detail. Yet at the highest possible temperatures, our predictive power fades. It is as if the universe has placed some of its deepest rules behind a barrier of extreme heat. Crossing that barrier will not be a matter of slightly better instruments. It will require new concepts and a new theory. This raises a natural question. Could anything in the universe today, or in its future, ever get close to the Planck temperature? The early universe clearly did, but only for a very brief instant after the Big Bang. In the cosmos we see now, the hottest known natural environments occur in violent astrophysical events. The cores of some supernovae reach billions of degrees. Gamma ray bursts and matter spiraling into black holes can heat gas to hundreds of billions of degrees. These numbers are immense, but they are still far below the Planck scale, which sits more than 20 orders of magnitude higher. Another place to look is in cosmic ray collisions. Ultra-high energy cosmic rays are particles, usually protons or atomic nuclei, that travel through space at nearly the speed of light. When they collide with atoms in Earth's atmosphere, the energies per particle can far exceed those we reach in any accelerator. In the most extreme recorded events, the energy of a single particle can be comparable to what you would associate with a temperature on the order of 10 to the power of 32 Kelvin. Here, we have to be careful. Calling this a temperature can be misleading. Temperature, in the thermodynamic sense, describes the average energy of a large collection of particles in equilibrium. A single particle with enormous energy does not make the whole system hot in that way. To reach something like the Planck temperature as a true thermal state, you would need a dense collection of particles all sharing that extreme energy range. Any system like that would emit radiation furiously and would probably collapse or transform into something else, such as a black hole, before it could settle into a stable, hot equilibrium. This is one reason why absolute hot is as much a gravitational limit as a thermal one. In a laboratory, our most powerful machine, the Large Hadron Collider, accelerates protons to energies of about 13 trillion electron volts each, creating brief temperatures of a few trillion degrees and forming quark-gluon plasmas for tiny moments. To reach the Planck scale, you would need to raise energies by about 1 trillion times, and you would need many particles at once, not just isolated collisions. That requirement places the goal far beyond any realistic engineering, unless we could somehow harness energy flows on the scale of stars or galaxies. Some speculative theories suggest that if our universe has extra spatial dimensions beyond the 3 we perceive, as in certain versions of string theory, the true quantum gravity scale might be lower than the traditional Planck value. That could, in principle, bring aspects of quantum gravity into reach at energies only a few orders of magnitude above those we can explore. Even so, lower in this sense would still mean vastly beyond our current capabilities. People have also wondered, at least in thought experiments, whether it might ever be possible to trigger artificial high-energy events on astrophysical scales, compressing large amounts of matter into tiny regions and injecting huge amounts of energy. In principle, that could push local conditions toward the theoretical ceiling. In practice, such scenarios remain far outside anything we can do, and firmly in the realm of speculation. If we imagine pushing an artificial system toward the Planck temperature, the obstacles are not just technical. The side effects would be severe. If enough energy were packed into a small enough region, the whole setup would likely collapse into a black hole. The experiment would end instantly, and depending on the mass involved, the collapse could affect more than just the immediate surroundings. This is why absolute hot looks less like a target we could ever engineer and more like a limit the universe protects with its own rules. Even if you could somehow heat a region to that scale, it might not remain a region in any useful sense. Space-time itself would be fluctuating so strongly that there would be no stable location, no fixed frame in which to define a temperature. The very act of forcing the system toward that limit could erase the structures you were trying to heat. The system would turn into something else before a meaningful equilibrium could form. Nature, however, seems to have reached such conditions at least once. The early universe, in its first tiny instant, passed through temperatures at or above the Planck scale. Some cosmological models suggest that similar conditions might arise elsewhere, in ways that are unreachable to us but still part of the broader picture. In some versions of eternal inflation, new pocket universes are constantly forming. Each one may begin in its own Planck-era state before cooling. In some higher dimensional models where extended objects called branes can collide, the aftermath of such a collision could also involve temperatures near the Planck range. These ideas are speculative, but they show that absolute hot might be a recurring feature of the wider cosmos. Even if we can only study its echoes, black holes add another layer to this story. At first glance, a black hole seems like the opposite of something hot. Nothing escapes from inside its event horizon, so it is easy to think of it as a cold, dark sink. That picture changed when Stephen Hawking showed that quantum effects near the horizon make black holes radiate. This Hawking radiation gives black holes an effective temperature. The surprising part is how that temperature behaves. The more massive the black hole, the colder it is. Supermassive black holes in galactic centers have temperatures only tiny fractions of a degree above absolute zero. The hottest black holes, in this sense, would be the smallest ones. A very small black hole would have a higher Hawking temperature and would radiate strongly in its final moments before evaporating. Hypothetical primordial black holes formed in the early universe could fall into this category. A tiny one finishing its evaporation today would release an intense burst of radiation, far hotter than any stellar core, though still far below the true Planck temperature. If we ask what happens deeper inside, our current theories reach their own limits. Classical general relativity says that matter inside a black hole collapses to a singularity, a point of infinite density and curvature where our equations break down. Most physicists think this point is a sign that a more complete theory is needed, not a final physical object. Quantum gravity may replace the singularity with a finite but extremely dense region, perhaps characterized by Planck-scale temperature and density. If so, black holes could contain enduring Planck-like conditions hidden beyond their horizons. We cannot access those conditions directly, but they would be part of the overall thermal story of the universe. The concept of a horizon is central when we think about heat and gravity together. A horizon is not a solid surface. It is a boundary in space-time beyond which events cannot affect a given observer. The event horizon of a black hole is one example. Cosmology gives another. In an accelerating universe, there is a cosmological horizon beyond which light emitted today will never reach us. Quantum field theory in curved space-time shows that horizons and temperature are linked. The presence of a horizon can make quantum fields behave in a way that looks thermal. Hawking radiation is one case of this connection. Another is the Unruh effect. According to the Unruh effect, an observer who is accelerating through what an inertial observer would call empty space will detect a bath of particles with a definite temperature. The faster the acceleration, the hotter this perceived bath. If you push the acceleration toward extreme values, the associated Unruh temperature rises. In principle, accelerations near the Planck scale could correspond to effective temperatures near the Planck temperature. This does not mean the vacuum itself is hotter in some absolute sense. It means that what we call temperature depends, in part, on the observer's state of motion when quantum fields and gravity enter the picture. Some speculative ideas, like white holes, the time-reversed solutions of black holes, or wormholes connecting different regions of space-time, extend the role of horizons even further. These objects are not known to exist in nature, but they appear in some mathematical solutions of Einstein's equations. If they are physically meaningful in some form, their boundaries might also carry thermal properties tied to extreme conditions. In any case, black hole and cosmological horizons already show us that geometry, quantum fields, and temperature are deeply connected. They hint that absolute hot is not just a property of matter, but also of space-time itself when it is pushed to its limits. At very small scales, space-time might not be smooth. Some approaches to quantum gravity suggest that on Planck scales, space-time resembles a kind of foam made of fleeting structures, tiny black holes, short-lived tunnels, and rapidly shifting curvature. In such a picture, horizons could appear and disappear constantly. Each tiny horizon would have an associated temperature. The Planck temperature could then be seen not just as a single extreme value, but as a characteristic scale woven into the restless behavior of space-time at its smallest grains. Because black holes combine strong gravity, high energy densities, and quantum effects, they serve as natural test beds, at least in theory, for ideas about absolute hot. Even if no real black hole ever achieves a true thermodynamic Planck temperature, their properties bring us closer to that frontier than anything else we can observe or model. They help us see how heat, horizons, and geometry interact near the edges of our current understanding. In the search for a unified description, string theory offers one of the most detailed frameworks. In string theory, the basic objects are not point-like particles, but extremely small strings. Different vibrational patterns of a string correspond to different particles. One mode behaves like an electron, another like a photon, another like a graviton. Replacing points with strings softens some of the infinities that appear when gravity is combined with quantum mechanics. But strings also introduce new thermal behavior. One key idea in this context is the Hagedorn temperature. The Hagedorn temperature is not the same as the Planck temperature, but it plays a related role within string theory. It appears as a sort of limiting temperature for a gas of strings. For ordinary particles, adding energy generally increases their average speed, and thus the temperature. For strings, as you add more energy, they can vibrate in more and more complex ways. The number of available vibrational states grows very rapidly with energy. Near the Hagedorn temperature, extra energy tends to go into exciting new modes and making longer, more massive string states, rather than increasing the average kinetic energy. The temperature rises more slowly and can approach a kind of plateau. This behavior is similar in spirit to a phase change, like water absorbing energy to turn into steam without its temperature climbing quickly during the transition. In string theory, passing the Hagedorn point may signal that the system is moving into a new phase where the usual picture of separate strings no longer works. In some models, this high temperature phase is better described in terms of black hole-like states or more fundamental structures, and the effective notion of space-time itself can begin to emerge from these deeper ingredients. In many versions of string theory, the Hagedorn temperature is not far below the Planck scale. That suggests that understanding what happens to strings at and beyond the Hagedorn regime could be a step toward understanding what happens at absolute hot in the broader sense. Some dualities in string theory mathematical relations that show how two very different descriptions can actually represent the same physics hint that heating a system of strings past the Hagedorn regime is equivalent to describing it in terms of black holes. Under this view, extreme heat and extreme gravity are two ways of talking about the same underlying phenomena. This is appealing because it links three major pieces: thermodynamics, quantum mechanics, and gravity. It also supports the idea that the Planck scale need not be a hard wall where everything stops. Instead, it might mark a transition into a different description, where the familiar language of particles, fields, and even classical spacetime is replaced by something more general. In that description, the concept of temperature may also need to be revised or extended. Of course, string theory, like other candidate theories of quantum gravity, is not yet confirmed. We cannot probe the Hagedorn regime directly. Testing these ideas will require both clever theoretical work and new ways of connecting them to observable phenomena. Still, the notion of a maximum or critical temperature that leads into new physics reinforces a central theme. At the highest energies, our usual thermodynamic intuition may no longer apply in a straightforward way. All of this leads to a deeper question. Why might pushing toward the Planck scale cause the very idea of temperature to break down? We are used to thinking of temperature as a universal quantity. We measure it in cups of tea, in the air outside, in stars, and in the cosmic background radiation. It seems to scale from the everyday world to the astronomical. It is tied to thermal motion, the jostling of particles in a system, and it feels almost too basic to fail. Yet near the Planck temperature, that may be exactly what happens. The everyday definition of temperature comes from statistical mechanics. In statistical mechanics, temperature is defined for a system with many degrees of freedom. You imagine a huge number of microscopic constituents, track how their energies are distributed, and define temperature as a measure of the average energy per degree of freedom when the system has had time to share energy and reach equilibrium. It is a bulk property, not something that belongs to a single particle. Near the Planck scale, this picture starts to unravel. The idea of a lot of particles may no longer apply in any familiar way. Energy density is so high that gravity is no longer a weak background effect. The gravitational field becomes a strongly dynamic part of the system. Space-time may be undergoing rapid quantum fluctuations, changing its shape and even its connectivity on scales far smaller than anything we can currently probe. In such a regime, the medium you are trying to describe may not be a stable space-time at all, but something more like quantum foam in which energy, geometry, and causal structure fluctuate together. Under these conditions, the usual notion of temperature as an average over well-defined motions in a fixed background starts to lose meaning. It is like trying to define the temperature of a liquid that is constantly turning into something else so quickly that the liquid phase never really exists long enough to have its own properties. At the Planck scale, the container, space-time, and the contents, fields, and excitations may both be changing too quickly and too deeply for equilibrium to form in the usual sense. Time adds another complication. Temperature, as a macroscopic concept, relies on the idea of time averaging. A system must have some interval over which it exchanges energy internally and relaxes. Many approaches to quantum gravity suggest that near the Planck scale, time itself may not have the smooth, ordered structure we assume. If time becomes granular or behaves more like a quantum variable, then the conditions needed to define equilibrium may never arise. The statistical tools of thermodynamics assume both large numbers of degrees of freedom and some kind of continuity in space and time. If space-time is fundamentally discrete at these scales, those assumptions may no longer hold. There is also an information-theoretic way to look at these limits. In modern physics, temperature can be viewed as a measure of missing information about the exact microstate of a system. A hotter system can be in more possible microstates, consistent with the same macroscopic conditions. So knowing its temperature tells you less about which detailed configuration it is in. At the Planck scale, however, the information capacity of a region may be bounded in a new way. The holographic principle suggests that the maximum entropy, the maximum number of distinct microstates inside a region, is proportional not to its volume, but to the area of its boundary measured in Planck units. If that bound is saturated, adding more energy cannot increase the number of accessible microstates beyond a certain point. The system's phase space is full. In that situation, pushing the temperature higher in the usual sense may not be meaningful. Black hole thermodynamics gives a related example. A black hole's entropy scales with the area of its event horizon, and its Hawking temperature is linked to its mass and surface gravity. A black hole of roughly Planck mass would be an object where quantum gravity, information bounds, and thermal concepts all meet. Beyond that, the most natural way to describe the system might be purely geometric, in terms of curvature and horizon structure, rather than in terms of temperature and ordinary matter. Some theorists suggest that it is more accurate to think of the Planck temperature not as the hottest possible state in a simple way, but as the point where thermal energy and space-time curvature become indistinguishable aspects of one underlying reality. At moderate conditions, one can talk about matter being hot within a space-time background. Near the Planck scale, matter, energy, and geometry may be inseparable. The degrees of freedom that carry energy and the degrees of freedom that define the shape of space-time could be the same entities. In that picture, asking for the temperature of the system may be like asking for the temperature of a bare gravitational field. The question does not match the underlying variables anymore. This leads to a broader conclusion. Temperature, despite its apparent universality, is an emergent property. It is extremely useful for gases, solids, plasmas, and even for describing horizons, as in black hole thermodynamics, because those systems have enough structure and stability to support a thermal description. But there is no guarantee that every possible state of the universe admits a meaningful temperature. At the cold end, quantum mechanics stops us from reaching perfect stillness. At the hot end, the very framework that allows us to define temperature may dissolve into something more fundamental. Even if temperature disappears as a useful concept beyond the Planck scale, the underlying system would still have properties. There would still be energy densities, curvature, topological features, and perhaps discrete building blocks of space-time. They would simply not map neatly onto our current thermal vocabulary. Just as classical mechanics had to be replaced by quantum mechanics for very small systems, physics near the Planck temperature may require not just modified equations, but a new set of basic notions about what exists and how it behaves. This is why the Planck temperature is best viewed as a conceptual boundary. It marks the point where a familiar and intuitive quantity stops being part of the language of physics as we know it. That is both a limitation and an opportunity. It shows where our tools fail, but it also points directly to where new theories must take over. Cosmology gives an important context for this boundary. The Planck epoch, the earliest phase of the universe we can sensibly talk about, lasted only about 10 to the power of minus 43 seconds. Before that, we lack a tested theory. Immediately after that instant, energy densities were still enormous, and if temperature was a valid concept, it was at or near the Planck scale. In this regime, the four known interactions may not have been distinct. Gravity, electromagnetism, and the strong and weak nuclear forces may have been unified into a single interaction. Particles, if they existed as separate excitations, were likely massless and interchangeable. Space-time was probably highly curved and rapidly changing. As the universe expanded, it cooled very quickly. Within an extremely short time, temperatures dropped enough for the strong force to separate from the others, then dropped further so that the electro-weak interaction split into the electromagnetic and weak forces. These symmetry-breaking events gave particles their masses and allowed matter to form stable structures. In this sense, the Planck temperature acts like a boundary condition at the universe's birth, the high starting point from which all later thermal history descends. The entire hierarchy of particles, atoms, stars, and galaxies emerged during and after this cooling. Thinking about absolute hot also raises questions about the long-term future. If the universe continues its accelerated expansion, it will cool over unimaginably long times. Stars will burn out, black holes will evaporate, and the cosmic temperature will approach a value very close to absolute zero. In that scenario, Planck scale temperatures would have been a one-time phenomenon, confined to the very early universe. Other models consider different possibilities. In a hypothetical big crunch, where expansion reverses and the universe collapses, densities and temperatures could rise again. In the final stages, conditions might approach the Planck scale once more. In cyclic models, where the universe goes through repeated phases of expansion and contraction, crossing the Planck regime could be a recurring feature, with each cycle passing through an extreme hot state before a new expansion. More speculative ideas even allow for black holes to act as seeds of new universes, with Planck-like conditions at their core acting as a kind of bounce into a new phase of expansion. In those pictures, Planck-scale physics would not be a one-time event, but a repeating element in a larger cosmic pattern. These scenarios are far from settled, but they highlight how the Planck temperature sits at key turning points in cosmological thinking. It is involved in discussions of the arrow of time, too. The second law of thermodynamics ties the direction of time to increasing entropy. Yet the early universe appears to have been in a very low gravitational entropy state, even though it was extremely energetic. As structure formed and matter clumped under gravity, gravitational entropy rose, even while the overall temperature fell, near a potential final collapse. gravitational and thermal effects could intertwine again in ways that touch the Planck scale. Taken together, these ideas underline that absolute hot is not just another large number on a scale. It is a pivot in the story of the universe. It marks where our current laws cease to be sufficient, where unification of forces and geometry becomes unavoidable, and where questions about information, entropy, and the nature of space-time come together. Understanding what happens at or beyond this boundary would likely illuminate not only the birth of our own universe, but the range of ways any universe might behave. For now, the Planck temperature remains out of reach experimentally and only partly described theoretically. Yet it already serves a clear role. It tells us where our present framework ends and where the next layer of physics must begin.